uh, the devices, two devices, optoelectronic devices. Those were the LDR and the LED. Okay. Today we are going to see another interesting optoelectronic device, and it is called as a photodiode. Now remember, what is the mechanism? Let us first of all understand the mechanism, how it works. Is the one note page visible to all of you? Hello? Hello?
Yes, sir.
Okay. So when we have a PN junction, so when PN junction is reverse bias, so when PN junction is reverse biased, you already know what happens when it is reverse biased. So what we have is the depletion region. This is P, this is N, and if I want to reverse bias it, it will be something like this. So in case of reverse bias PN junction, what happens? There is a very small current called as reverse saturation current, right? We used to call it as IS. So for a conventional diode, you have small current which flows like this. Okay, so this is V, this is I, and this current actually increases with increase in temperature. You all know that, all right? Yes or no, guys? Hello.
Yes, sir.
Why aren't you responding? So we have the reverse saturation current, and this reverse saturation current is influenced by temperature. You know that. You know that it doubles for every 10 degrees Celsius rise in temperature. Okay. Now the mechanism over here is that who is creating this current? I mean, who is responsible for this current? Reverse saturation current. Yes. Or what is the? I mean, who constitutes this reverse saturation current? This reverse saturation current is because of the minority charge carriers. Because we already know one thing, that reverse bias will support minority charge carrier current. Okay, so reverse bias actually enhances or supports minority charge carriers. Means that holes from P type are going into this region, electrons from this region so we have electrons here, but they are very few, and we in type we have minority charge carriers as holes. So this actually is responsible. So minority carriers from P type, which are electrons, go into N type and this. So we have some current which flows and which we call as the reverse saturation current. Now we know that this is influenced by the change in temperature. As temperature increases, more energy is given to the minority charge carriers. Of course, they are more minority charge carriers are generated because of temperature, and so the current increases. This is the phenomenon which we have already seen. Now, a similar kind of thing will happen, or same effect will happen if if the junction is illuminated. So if I impinge light on this, what is light ultimately? It is collection of photons. These photons give energy to these minority charge carriers, and they get more minority charge carriers will be generated. So this is basically the working mechanism. If the junction is eliminated, it increases the number of charge carriers, and hence the reverse saturation current also increases. These types of diodes are special diodes which are called as photodiodes. Okay, the symbol of a photodiode is something like this. So again, it is enveloped, and then you have arrows pointing towards them. So this is basically the symbol of a photodiode. If you look at the characteristics, slightly different characteristics, because here we have 0 volts over here. So this is 0. Okay, this is, let us say, point. So point 2. This is point 4, and this is point 6. So I've shifted the axis this way. Now this is where the diode is forward biased slightly. Okay, not much. And in this region we have reverse bias, so it is VR. Okay, so now I can just mark it here. This is negative voltage, please remember that. That is reverse bias. Okay, and if you try to draw the curves, it will look like this. So it starts with, let us say, here. Okay, let me first of all mark the current. So remember, this is not origin. I'm just so this current is in microamperes. Remember this. All right. If I try to draw the curves, I get something like this. So this is for a particular value of illumination H as let us say 5 milliwatts per centimeter square. As you increase the illumination, subsequently you get different curves. Alright. So this curve is for H as 10 milliwatt per centimeter square. So if I go on increasing the illumination, subsequently the current also increases. Okay. So it increases like this. So these are the characteristics. So for different values, H as let us say 15 milliwatt per centimeter square. This is H. I mean so on. I mean it goes on increasing. So this is H is let us say 20 milliwatts per centimeter square. So what you see here is that as you go on increasing the illumination, the current basically increases. Of course, the current is very very small, but there is a increase, substantial increase relatively. Okay, earlier it was 10 microamperes, and let us say for here 20, it has become 60 microamperes, and so on and so on. So you have this kind of characteristics. Okay, have you understood this?
Yes, sir.
Okay. Now let us see the specifications or typical specifications. So we have the power dissipation, something called as VOC, that is the open circuit terminal voltage. Then we have BR max, that is maximum reverse bias that you can apply. ID max, that is a dark current. Then you have IL, where VR is specified as 2 volt. This is a specific, I mean, this is a special, I mean, a typical case, typical diode with illumination as milliwatt, 5 milliwatt per centimeter square. Then we have something called as the response time, PR, and the wavelength at which it is sensitive. So typical values are 100 milliwatt here, 350 millivolts, 100 volts, 2 nanoampere, 10 microampere. Response time is 2 nanoseconds. Then we have nanometer. There is one more parameter, the sensitivity S, which is 7 microampere per milliwatt centimeter square. So these are the typical specifications of a photodiode. Let us have a quick look at the construction. So this is the contact. Okay. This is again contact. But before that, we have this is the P-type material. Here you have the metallic contact. Here you have this is the SiO2 layer. So you must be reminded of the MOSFET. So this green thing is the SiO2. Here you have the light, rather the window for the light. So this is the metal contact, also called as ohmic contact. This is also metal contact. This is P-type region, and this is N-type region here. So this is the construction of a photodiode. So if you look at another view, so you have a glass lens here, and then you have the terminals like this. So this is how it is fabricated. Okay. So what we have here, a thin, heavily doped p-type layer is situated at the top where it is exposed to the incident light. Okay. This junction depletion region penetrates deeply into the lightly doped n-type region. So remember that this n-type is lightly doped, p-type is heavily doped. So the depletion region will extend more in the n-type region. Now this is in contact with the lower heavily doped n-type layer which connects to metal film contact. So you have another layer, I missed it. So there is another layer here of n-type, but it is heavily doped. Okay, I'll use a different color. So this is again n-type, but heavily doped. Okay, so this is basically the construction of a photodiode. Now remember that photodiode is always to be used in the reverse bias condition. Guys, am I audible still?
Yes, sir.
Okay. So most of the times we have to use it in the reverse bias condition. Very simple application I'll show you. So you have to turn on a transistor, okay, based on the light. So what we can do is we can use the photo diode like this. Please see that it is a reverse bias and it is like this. So this is your plus VCC. So this is one of the ways in which you can use the photodiode. Okay. Then we come to another interesting uh, component called as the phototransistor. Okay. So phototransistor is very similar to your ordinary bipolar junction transistor, except that its collector base junction is constructed like a photodiode. So okay, when the base is open, you have this kind of. And then we also said that IC is equal to 1 plus beta into ICBO, because this happens to be the common emitter configuration. All right. So in a similar way, you have the same kind of effect is utilized in the phototransistor. So instead of the base, you have light which is incident or which can be made incident on this particular base, and this actually creates the ICBO and in general the collector current. Okay, so this is a basic operation. So in phototransistor, your ICBO acts as the base current. Now since your ICBO will increase, because ICBO also is a reverse saturation current. So this also increases, and if this increases, collector current also increases by 1 plus beta times. Okay, and that is how your light change in the light will create a change in the collector current. So IC is proportional to the illumination. Okay, so for a given amount of illumination on a small area, this photo transistor will provide much higher output current than the photodiode. If you see carefully that the photodiode was, yeah, it was sensitive to light, of course, but the change in the current was in microamperes, which was comparatively small. But in case of transistors, phototransistors, this change is quite high. Okay, so we can say that the phototransistor is more sensitive to light than the photodiode. Okay, let us see the construction quickly. Uh, this is the symbol. This is the metal contact, just like previous construction. This is N type, lightly doped. This is N type, we call it as N plus, which is heavily doped. Very similar construction, small.
अमेरिका तो अपने आप को सही करे, अमेरिका तो अलग हो ही गया.
ये क्या हो रहा है? So again, this is SiO2 layer. This is again the metal contact. You have the P-type material, and again you have so this is N-type. So this is emitter. This terminal is emitter.
सर स्क्रीन फ्रीज हो गई है.
Is it?
यस सर.
Okay. Share it again. Okay now?
यस सर.
So again you have light, which is falling here. Again, this green area is the SiO2 layer. This is P, which is the base. And this is the collector. So you have NPN structure. Okay. All right. Let us quickly see the characteristics. This is the volts. This is collector current in milliampere. This is in volts. So you'll see that it resembles, the curves actually resemble your transistor. So this is 4 milliamperes. And we have 8 milliamperes, 12 milliamperes, 16 milliamperes, and so on. And of course, it is sensitive to different values of illumination. So it's 25 milliwatt per centimeter square. This is 20 milliwatt per centimeter square. This is a typical, let us say, value, and so on. Okay. Here it is, which is 10 milliwatt per centimeter square. Milliamperes. Okay, and which is much significant as compared to the photodiode. So phototransistor is more sensitive to light than the photodiode. So it is most of the time it is preferred. Okay, let us see specifications of a typical device. Again, the power dissipation. And you have VCE max. That is the maximum voltage you can apply across the collector and emitter. Then you have ICE O max. That is a dark when VCE is 10 volts, a typical condition. IC minimum when VCE is 10 volt, sorry, it's 5 volt. And intensity of light is 5 milliwatt per centimeter square. And the response time, sorry, it's a rise time, then you have the fall time, sensitivity, and wavelength. So the values, typical values are like 200 milliwatt, VCE is 40 volts, it is 100 milliampere, sorry, 100 nanoampere. This is 3 milliampere. Rise time is 5 microseconds. Fall time is 8 microseconds. Sensitivity is 500 microampere per milliwatt centimeter square. And again, sensitive to 900 nanometer wavelength. Okay. So what is this rise time and fall time? Let us quickly see that. So whenever I am using the transistor as a switch, ideally, an ideal switch, which is very, very instantaneous, okay, can be said to have characteristics like, okay. First of all, understand one thing, that if I want to use the transistor as a switch, this is going to be the voltage across the device. Okay, so if it is supposed to be like a switch, if it is supposed to be used like a switch, now tell me one thing. If let us say if I apply 10 volts here, okay, of course there is some current here, there is some resistance here, and so on and so forth. Now, if I open the switch, if you find out the voltage over here, this is output, let us say V1 or voltage at this point. So, if you have voltage at this, what will be the voltage at this point when the switch is open? What will be this voltage? When the switch is open, if you measure voltage between these two terminals, what will it be? Or across the device, let us only concentrate on whatever is across the device. So across the device बोले तो यहाँ पे. What will be the voltage here, guys? It will be equal to the entire voltage, 10 volt. Now, if I close the switch, what will be the voltage across the device? Yes, it will be equal to 0. Are you getting it? हेलो.
सर 10 से 0 कैसे हो जाएगा?
अरे वही तो मैं पूछ रहा हूँ, आपको समझ में आ रहा है या नहीं आ रहा है? आई एम रियली फेड अप of asking n number of times whether you are able to hear me or not. आपका रिस्पॉन्स ही नहीं आता है. अरे ये स्विच क्लोज किया ना?
यस सर.
ये स्विच अगर क्लोज किया मैंने, तो स्विच के अक्रॉस वोल्टेज कितना रहेगा? शॉर्ट हो गया ना ये?
यस सर.
तो कितना होगा वोल्टेज?
सो 0.
हाँ, अभी समझ में आ रहा है नहीं आ रहा है?
यस सर.
So when a switch is open, voltage across it is full volt, whatever is applied, and when the switch is closed, voltage across it will be 0. So if I want to use a transistor, again the transistor is not an ideal switch, but if you see carefully that the transistor, if it is used in the saturation region, okay, let us quickly plot the characteristics. This is VCE, this is IC, and you have the characteristics like these. So इस area में you call it saturation, no?
Yes
And
sir.
this you call, after this IB equal to 0, you call this black region as cutoff. ठीक है? तो ट्रांजिस्टर अगर सैचुरेशन में, तो उसके अक्रॉस वोल्टेज कितना होगा? वेरी स्मॉल. दिस इज अबाउट 0.5, 0.3 to 0.5 volts, which we call as VCE sat, or saturation voltage. So as if, so if you place the transistor in saturation, it is as if it is what? Open or closed switch?
Sir, pardon.
If I place the transistor, if the transistor is in saturation, तो उसके अक्रॉस वोल्टेज कितना है? ये VC sat, ये बहुत कम वोल्टेज है ना, nearly equal to 0.3 volts.
Yes sir.
So it is as if the transistor is open, and the switch is open or closed. It is as if it is
open. Oh, sorry, closed.
It is closed. So the transistor will act as a closed switch. Now, if I
Yes,
place
sir.
the transistor somewhere in the saturation, यहाँ पे, तो क्या होगा? It is as if the transistor is
Sir,
off.
open.
As if the transistor is switched off or open, है ना? देखो यहाँ
Yes,
पे,
sir.
यहाँ पे in this case, if I fix the somewhere over here, you'll see that significant amount of collector current flows, but voltage across the device is very small, very small. Whereas in this case, the voltage across the device is large, complete voltage of VCC, but current flowing through that is almost 0. समझ में आ रहा है कि नहीं आ रहा है?
Yes sir.
So if I have an ideal switch, and if I, let us say, अभी तो मैं I'll use with respect to time, and if I open and close the switch, what will be the voltages across the switch, ये देख लेते हैं. Okay, so when the switch is open, उसके अक्रॉस मैक्सिमम वोल्टेज होगा, है ना? ये जो भी है V maximum. This is when the switch is closed, switch is open. और यहाँ पे सडनली मैंने स्विच को ऑफ कर दिया, तो उसके अक्रॉस अभी देखो वोल्टेज कितना आ रहा है. आई विल स्विच इट ऑफ फॉर सम टाइम, एंड देन अगेन आई विल स्विच इट ऑन. स्विच का ऑपरेशन ऐसे ही होता है ना, यू कैन, ठीक है? ये
Yes, sir.
इंस्टेंटेनियस स्विच हो गया. So this is the voltage across switch. ट्रांजिस्टर के केस में क्या होता है कि you have this VCE max and then it doesn't suddenly switch off. Even if I try to switch it off, it will take some time to switch off. फिर यहाँ पे जाके V saturation को जाएगा वो, and if I switch it on, it will again take some time for me to switch on. So ये practically ऐसे होता है.
So you are not audible.
And similarly, the time that it takes to go from 90% to 10% while going down, इसको बोलते हैं fall time. So it depends, right? Like if the rise time and fall times are very, very small, we can say that the device is very fast. Okay? समझ में आ रहा है कि नहीं आ रहा है?
Yes, sir.
इसका टिपिकल एप्लीकेशन देख लेते हैं. So VCC रिले को ड्राइव करना है. रिमेंबर द रिले का सिंबल. We drive it with a transistor which will be used as a switch, and I'm going to activate it with a photo transistor. Okay, don't worry even if you don't understand this, but the thing is that if you have light, now okay, if there is no light here, there is no current flow. So there is no base current for the transistor. If the base current IB is 0, where will this transistor be? Call this as T1, call this as T2. So base current transistor का 0 है, तो क्या होगा? Transistor is in cutoff, है ना? If it is in cutoff, it is acting as a switch which is turned off. So there is no current flowing through this relay coil and the relay is not activated. But as soon as this current, this light is incident on the photo transistor, इसका collector current will flow, which is nothing but the base current here. Of course, there is some current flowing here, but doesn't matter. So we get a base current, and as soon as we get the base current, you turn on the transistor. Rather, because of the base current, the transistor is turned on. This current will start flowing, and it will act as if I have closed the switch. Okay.
Yes, sir.
So this is basically how the photo transistor is used. Okay. I think I'll stop here for today. Any doubts? Any questions?
No, sir.
I'll be completing all your units and then we'll go for a brief revision because some things are remaining which we will complete at the end. All right.
Yes, sir.
Yes, sir. Actually, we need revision, sir.
Sorry?
Actually, we need revision.
क्या बात कर रहे हो? मुझे सुना ही नहीं दे रहा है ठीक से. जोर से बोलो.
Nothing, sir.
Sorry? अरे बोलो.
Sir, nothing.
Nothing.